The Earth System, a video series for educational institutions for free use presented by the German Geological Society, the DGGV. Hello everyone and welcome to another episode of the Earth System video series. As with all other videos, I would like to point out the opportunity to write me if you have any questions or comments. My email address is written down in the first page of the video or on the website. This video is about the structure of the lithosphere. How is it composed? How thick is it? And how is it related to plate tectonics? In the previous video, I already explained that the outer shell of the Earth, which we call the lithosphere, is only a very thin layer. The distance to the center of the Earth is almost 6,400 kilometers. On the other hand, the lithosphere is on average just 100 kilometers thick. That is less than 2%, or in other words, 2/100th of the Earth's radius. But this lithosphere protects us from the hot and fiery magma that pushes up from the Earth's mantle. Let's have a closer look at this lithosphere. Here in this figure, which I already showed in the first video, there is no exaggeration. It shows the proportions as in nature, and you can see the extremely thin lithosphere about the Earth's mantle again. And at this point, where a continent and an ocean lie next to each other, here it is South America and next to it the Atlantic Ocean. Let's zoom in because in this scale we cannot see anything. This is a strongly exaggerated representation of this situation, as I pointed out in the first video. Here you can see that there are two different types of lithosphere, continental and oceanic. Continental lithosphere consists of continental crust on top and underneath the so-called lithospheric mantle. And oceanic lithosphere consists of oceanic crust on top and again lithospheric mantle underneath. The lithospheric mantle is the same for both, but it can be thicker under the continental crust than under the oceanic crust because the lithospheric mantle is older there. In a later video, I will explain in more detail how the lithospheric mantle evolves in time. Both the continental and oceanic lithosphere are entirely solid, and this is an important requirement for plate tectonics. Only the asthenosphere, which lies beneath the lithosphere, contains molten rock material. However, temperatures well above 1000 degrees Celsius prevail here, and this causes partial melting of the rock. This is why the asthenosphere is soft and flowable, which is necessary for plate tectonic function. Let's take a look at some of the most common rocks in the lithosphere. Oceanic crust is largely made up of basaltic rocks, which include surface-flowing basalt as a volcanic rock, which mostly emerges from volcanoes at great depths on the seabed, and we find pillows there, and gabbro and microgabbro or dolerite. The gabbro is of the same composition as basalt, except that gabbro does not come to the surface. It solidifies in the depths and needs therefore much more time to cool down, which is the reason that individual crystals can form there, instead of the formation of volcanic glass. Eventually, it becomes a coarse-grained rock, namely gabbro, which consists primarily of minerals like feldspar, pyroxene and olivine. The oceanic crust is made up of gabbro and dolerite in its lower part. A typical rock of the continental crust is granite. Similar to gabbro, it solidifies as a rock at depth and therefore also consists of many crystals. However, these are mostly lighter minerals than with gabbro. Granite also contains feldspar, but it has mainly quartz and mica that makes the rock light. Granite is a very common rock in continental crust, but almost not at all in oceanic crust. And sediments and sedimentary rocks are also typical of the continental crust in the upper part. A sandstone is shown here as a representative, but there are of course many others. such as limestone or claystone, etc. The lithospheric mantle is made up of rocks called peridotites, which primarily contain olivine and pyroxene as minerals. The asthenosphere beneath the lithospheric mantle is made up of exactly the same rocks or minerals. However, the difference is that the lithospheric mantle is completely solid, whereas the asthenosphere contains molten rock and therefore has a different physical state, which is why it does not belong to the lithosphere. The lithospheric mantle is part of the Earth's mantle because there is no difference in composition to the asthenosphere. At the same time, however, it is part of the lithosphere, which is divided into many lithospheric plates, as geologists call them, spread over the entire Earth. These are exactly the plates that we look at in plate tectonics and that can move on the soft asthenosphere. In summary, it remains to be said that the Earth's plates consist of lithosphere and therefore always have a portion of crust and a portion of lithospheric mantle. The lithospheric plates are an elementary part of plate tectonics. Looking at the 3D block diagram with the lithospheric plates of South America and Africa, we can see that the plates contain both continental and oceanic lithosphere. There isn't necessarily a plate boundary in between those two different types of lithosphere. The South American and African plates each contain half of the Atlantic Ocean. There are also plates that consist primarily of oceanic lithosphere, such as the Pacific plate, but actually all plates, including the Pacific, contain both continental and oceanic lithosphere. This also makes it clear that the boundaries of a plate do not depend on whether it is oceanic or continental lithosphere. There are other factors responsible for this, and I will look at this in more detail in some of the following videos on the plate boundaries. In the next video, I will first have a look at isostatic compensation. This is, like the structure of the lithosphere, a basic principle that should be understood in order to understand plate tectonics. Isostasy, which is based on the natural force of gravity, is one of the cornerstones of all tectonic movements on Earth. And then I will continue with plate boundaries and hotspots. This time, thank you for listening, and I'll be happy if you stick around. I recommend continuing with the video on isostasy.